Search for patterns and coincidences has always been a very well studied subject matter on scientific research. As an interesting example, we can quote the Similarity Texters website. Those simple motivations will give us the starting point of our presentation. Hi everyone, I'm Rodrigo Lambert, and I will talk about the symbolic case of matching strings in encoded sequences. First of all, I have to mention that this is a joint work with Adriana Coutinho and Jérôme Rousseau. So we will start on the board with some history on the problem. The first motivation was to compare DNA sequences. In 1985, Richard Reicha and Michael Waterman studied the longest common substring problem. It is defined like this. For two given sequences, let's take a look on the first n symbols of each one and find the longest common substring between them. Then you can tell this quantity mn. As an example, we take two 21-sized DNA strings. One can observe that these two common substrings are the biggest ones. Therefore, in this case, we say that M21 is equals to 4. Now let's cut the last 5 symbols on each string. One can observe that in this case, M16 is equals to 3. This in fact suggests a non-decreasing behavior on Mn. In fact, the authors proved that for large values of n, Mn behaves as 2 times log of n. Studying the shortest distance between two orbits in dynamical systems, Barro, Liao and Rousseau provided a generalization for these results for exponential alpha mixing and polynomial psi mixing processes. That's the paper I mentioned, by Vanessa Barros, Ligmin Liao and Jérôme Rousseau. And now we put a question. What about if we pass our sequences through an encoder and then try to investigate the same quantity? In other words, what about the longest common substring problem for encoded sequences? Let's go to our definition. We encode X and Y and do the same thing as before. We look at the first n symbols of each one and try to find the longest substring that appears in both n strings. We call this of MNF. We remark that f is a measurable function from a set of sequences to another one, and if f is the identity function, we recover the classical longest common substring problem. We are finally in position for stating our main result in this presentation, which is a law of large numbers for MNF. If p is the source measure, then the following limit holds for almost every pair of realizations of the process, where f star p is the push-forward measure that defines the law of the encoded process, and h2 f star p it is Rényi entropy. So let's remember our main result and let's state conditions under it holds. After that, we will explain which one with more detail. The first condition is on the existence of Rényi entropy. We recall that since f star p may be a non-stationary measure, find its Rényi entropy is not a trivial problem. The second condition states that the original process must be exponential alpha mixing or polynomial psi mixing. The third condition controls the deformation of strings that our encode can cause. The object of first condition is the Rényi entropy. Let's define it. The lower Rényi entropy is given by the following limit. On the other hand, the upper Rényi entropy is given by its lim sub. If they coincide, we have the existence of Rényi entropy, which is given by the common value. Recall that here the sums were taken over all k-strings with symbols on the alphabet key. Before stating the second condition, let's emphasize the intuition of mixing stochastic processes. Mixing is a kind of long-time memory loss property, in the sense that if two sets are separated by a big gap G, they behave as independent sets, so we can compare somehow the probability of intersection with the product of their probabilities. Actually, we want to make small this quantity or even this quantity when it makes sense. Formally, we define alpha of G in the same that way and psi of G like this, and we say that when alpha goes to 0 exponentially fast in G, the system is exponentially alpha mixing, and when psi of G goes to 0 polynomially fast on G, we say that the system is polynomially psi mixing. Finally, third condition is a condition on our encoder. It asserts that the encoder cannot deform too much the strings, in the sense that we can compare the order of the lengths of its images and pre-images. Since we stated our main result, let's go to an application for it. Imagine a situation in which we put weights on the symbol. Looking to our former example, let's imagine that each letter has a weight. In this case, we can see that V of A is bigger than V of C, which is bigger than V of T, which is bigger than V of G. In this context, the value of a match is given by the sum of the weights of the letters that compose it. We have then defined a quantity that studies matching with scores. This quantity has appeared in this paper by Richard Arecha, Priscilla Morris and Michael Waterman, and they were motivated by this game called Scrabble. They proved that the matching with score function behaves as 2 times log of n divided by minus log of p, where p is a quantity that satisfies this last line here. Bringing the problem to our context, we can construct the following encoder. Each letter is repeated v times, where v is its weight. With this particular code, matching strings in encoded sequences and matching with scores become the same problem. Therefore, we generalize their result to exponentially alpha mixing or to polynomially psi mixing processes. In particular, if P is an irreducible and aperiodic Markov chain, we get, by the last line, this quantity is equals to this one. By our main result, this quantity converges to this one, and in this particular case, this last quantity is equal to this one. At this time, I have to mention that this presentation treats a particular case on the shortest distance between two encoded orbits, which is studied in the following paper. So I ask you, please read it. Finally, I will use a Scrabble message to say, since it's possible, work from home. Thank you very much for watching and stay safe. Bye.